Download this code from codegive.com, link in the description below. Developing real-time web apps with the arcgis API for JavaScript, a comprehensive tutorial. This tutorial guides you through building a real-time web application using the arcgis API for JavaScript. We'll focus on using WebSockets and server-sent events, SSE, to push data updates to the map in real time. We'll cover various aspects including setting up a server, handling data updates, integrating with the arcgis API, and optimizing performance. Prerequisites **** basic knowledge of JavaScript, HTML, and CSS. ** familiarity with web development concepts, DOM manipulation, event handling. * basic understanding of arcgis Online or arcgis Enterprise, for map services and credentials. * node.js and npm installed, for our server-side component. * text editor or IDE, Visual Studio Code recommended. * arcgis developer account, for API key. Sign up for a free one at https://developers.arcgis.com/ https://developers.arcgis.com. Overview of real-time web applications with arcgis API for JavaScript. Real-time web applications display data that changes frequently and require updates to be reflected almost instantaneously. Examples include tracking vehicle locations, fleet management. Monitoring sensor readings, environmental monitoring. Displaying live traffic conditions. Showing social media activity on a map. Visualizing weather patterns. The arcgis API for JavaScript provides tools to display and interact with geographic data. Combining it with real-time data streaming technologies enables you to build dynamic and responsive applications. Key technologies ***. arcgis API for JavaScript *** a JavaScript library for creating interactive web maps and GIS applications. WebSockets *** a bidirectional communication protocol over a single TCP connection. Allows for real-time data exchange between the client and server. Suitable for applications with constant data updates and low latency requirements. Server-sent events, SSE, a unidirectional communication protocol where the server pushes data updates to the client. Simpler to implement than WebSockets and suitable for applications where the client only needs to receive data. Node.js, with Express, a JavaScript runtime environment for building server-side applications. We'll use it to handle data updates and broadcast them to connected clients. GeoJSON ***, a standard JSON format for encoding geographic data structures. We'll use it to transmit geographic features to the arcgis API. 2. Project setup and structure. Let's create a project directory structure. 3. Setting up the backend, node.js server. 1. Initialize the node.js project ***. Navigate to the server/directory in your terminal and run. This creates a package.json file with default settings. 2. Install dependencies ***. Express, a web application framework for node.js. *WS, a WebSocket library for node.js. Nodeman, automatically restarts the server when file changes are detected, for development. 3. Create server.js**. Explanation ***. We create an Express app to serve static files, later. We create a WebSocket server, WSS, that listens on the same port as the Express app. The WSS.on connection handler is called when a new client connects. Inside the connection handler, we can send messages to the client, ws.send, and receive messages from the client, ws.on, message. Asterisk we use setInterval, to simulate real-time data updates. In a real application, you would replace this with data from a sensor, API, or other source. The GeoJSON data simulates a point feature with updated coordinates and a timestamp. Asterisk the GeoJSON data is converted to JSON and sent to the client with a type, feature update to signal that this is a feature update. For update package.json with a start script asterisk. Add the following to your package.json within the scripts section. 5. Start the server asterisk. In your terminal, still in the server/directory, run. You should see server listening at http://localhost 3000 in the console. 4. Setting up the frontend, arcgis API for JavaScript client. 1. Create index.html, script.js, and style.css in the client/directory. 2. Client/index.html asterisk. Explanation asterisk. Asterisk includes the arcgis API for JavaScript CSS and JavaScript files from the CDN. Make sure the version, 4.29 here, matches the version you want to use. Check https://developers.arcgis.com/javascript/latest/ https://developers.arcgis.com/javascript/latest for available versions. Asterisk includes a custom CSS file, style.css. Asterisk creates a div with the ID view div where the map will be displayed. Asterisk creates a div with ID info div where we will display the feature information. Asterisk includes the main JavaScript file, script.js. 3. Client/style.css asterisk. Explanation asterisk. Asterisk sets the map container, view div, to fill the entire browser window. Asterisk styles the info div to be a semi-transparent box in the top left corner. 4. Client/script.js asterisk. Explanation asterisk. Asterisk requires the necessary modules from the arcgis API for JavaScript. Asterisk creates a map and map view to display the map. Replace your _API_ key with your actual arcgis API key. Asterisk creates a graphics layer to hold the real-time features. Asterisk establishes a WebSocket connection to the server at ws//localhost 3000. Asterisk the socket.add event listener, message, handler is called when the server sends a message. Asterisk if the message type is feature update, it parses the GeoJSON data, creates an arcgis graphic object, adds it to the graphics layer, and updates the info div with feature information. Asterisk important, graphics layer.remove all, clears existing graphics before adding the new one. This is the simplest approach for a single updating feature. For multiple features, you'd need a more sophisticated approach to update only the changed features, example using feature IDs. Asterisk includes error handling for the WebSocket connection. V. Serving the frontend, Express. To serve the frontend files, HTML, CSS, JavaScript, we need to configure the Express app. Add the following lines to server/server.js before the server.listen, call. 6. Running the application. 1. Start the server asterisk if it's not already running, navigate to the server/directory and run npm start. 2. Open client/index.html in your web browser. You should see the map displayed. After a few seconds, a point graphic will appear and update its location every 3 seconds. The info div will display the timestamp and value of the current feature. 7. Using server-sent events, SSE, instead of WebSockets. If you only need to push data from the server to the client, unidirectional communication, server-sent events, SSE, provide a simpler alternative to WebSockets. Here's how to adapt the example. 1. Backend changes, server/server.js. Key changes ***. We create an express route/events that handles SSE connections. **. We set the appropriate headers, content type, text/event stream, cache control, no cache, and connection, keep alive. ** We use rest.write to send SSE messages in the format data, JSON data \n\n. ** We handle client disconnect ions, req on, close, to stop sending events and prevent memory leaks. **CORS ** We've included CORS middleware. You'll likely need this to avoid cross-origin resource sharing issues in the browser. Install it with npm install CORS. Adjust the origin in CORS, for production. 2. Front-end changes, client/script.js. Key changes ***. We use new event source, http://localhost 3000/events, to establish the SSE connection. ** We listen for on-message events. The event.data property contains the data sent by the server. * Error handling for the event source is included. 3. Stop the old server and restart it, npm start in the server directory, reload client/index.html in your browser. You should see the same behavior as with WebSockets, but using SSE. 8. Handling multiple features and optimizing performance. The above examples update only a single feature. For a real-world application with many features, you'll need to optimize performance. 1. Use feature IDs ** assign a unique ID to each feature. When the server sends an update, include the feature ID. On the client, you can then update only the specific graphic with that ID, rather than clearing and re-adding all graphics. 2. Spatial indexing. For large datasets, if you have a very large number of features, consider using spatial indexing on the server side to efficiently find features within the map extent. 3. Clustering ** If displaying a dense collection of points, use clustering to reduce visual clutter and improve rendering performance. The arcgis API provides built-in support for clustering. 4. Web workers. For heavy computation, if you need to perform complex calculations on the client side, example buffering, spatial analysis, offload those calculations to web workers to prevent blocking the main thread and maintain a responsive user interface. 5. Use dedicated arcgis services * for very high volume data streams and persistence. Consider using arcgis Velocity, part of arcgis Online or arcgis Enterprise, which is specifically designed for real-time data ingestion, processing, and visualization. You can publish real-time feature layers and directly connect to them from your JavaScript application. 9. Advanced topics. * Authentication and authorization * Secure your WebSocket or SSE endpoints using authentication and authorization mechanisms, example JWT, OAuth. * Error handling and retry logic * Implement robust error handling on both the client and server to gracefully handle connection failures and data inconsistencies. Consider adding retry mechanisms for reconnecting to the WebSocket or SSE endpoint. * Data transformation and enrichment * Use server-side processing to transform or enrich the real-time data before sending it to the client, example calculating derived values, geocoding addresses. * Real-time geoprocessing * Trigger geoprocessing tasks based on real-time events and display the results on the map. This can be used for real-time spatial analysis, such as identifying areas affected by a natural disaster. Mobile optimization. Ensure your application is optimized for mobile devices by using responsive design techniques and minimizing data transfer. Example, updating multiple features with IDs. Server-side, server/server.js, modified. Client-side, client/script.js, modified. Key changes server-side maintains a features object to store the GeoJSON data for each feature, keyed by its ID. Sends an initial data message to the client upon connection, containing all initial feature data. When a feature is updated, the server sends a feature update message containing the updated GeoJSON data, including the feature's ID. Client-side maintains a feature graphics object to store the arcgis graphic objects, keyed by feature ID. On receiving the initial data message, it iterates through the features and creates an arcgis graphic for each one, storing it in the feature graphics object. On receiving a feature update message, it checks if a graphic with the corresponding ID already exists. If so, it updates the graphic's geometry and attributes. If not, it creates a new graphic. This shouldn't happen in this example but is good practice. The graphics are updated directly now, rather than clearing and redrawing the entire layer, leading to performance improvements. This example demonstrates how to efficiently update multiple features in real time by using feature IDs and updating existing graphics directly. Remember to replace your _API_ key with your actual arcgis API key. This is a more realistic pattern for building real-world real-time applications. This tutorial provides a solid foundation for building real-time web applications with the arcgis API for JavaScript. Remember to consider the specific requirements of your application, optimize performance, and implement robust error handling to create a truly compelling and informative user experience. Good luck.